Okay, so as you saw in my message, I'm talking about spectrometer architecture today, as was requested by David way back. Specifically, our type of spectrometer, the hyperspectral Pushbroom spectrometer. If you want to add an additional type, I guess we're talking a grading GRISM mechanism as opposed to a prism. No, GRISM as opposed to a grading or prism. But okay. So I have drawn an infinite line on here that will represent the optical axis. So pretend that this side is the ground, and then this is our payload. Okay, so with that, I've drawn a lens here. We know that our four optics is pretty complicated, right? It's got all sorts of lenses inside it that, like adjust for things like aberrations. Did I freeze for a second or did David?
I think David froze.
Okay, good. Okay, I'm good. Okay, cool. So
sorry, I have bad Wi-Fi right now.
Oh, no worries, no worries. I was just making sure I didn't freeze. We won't deal with those. What we'll do is just pretend that everything is just one lens. If you were here for the bits where I talked about the lenses, so we are 500 kilometers up in the orbit, right? So this means that let's try it like this, that our object distance is 500 kilometers. Now, if you look at this, our payload is what? Like 2u, which means this is at most 20 centimeters. So that means this 500 kilometers is essentially infinity. So we'll just call this infinity. That's pretty reasonable. So what do we know about light coming from infinity? It is parallel. And there's a specific way in which it's parallel. It doesn't mean that all of the light rays entering the system is parallel. It means that light from each point of the object that you're looking at is parallel. So let me explain that. So you can have light. I need water. Okay, my voice is not better. We can have light coming from, let's say up here. We can have light coming from down here. Those are not parallel, but the thing is, we're gonna have, how should I draw this? Let's say that, at infinity, we have this object that looks like this with respect to the axis, like this tall. What it means is that light from each point, like let's say light coming from here, pretend this is infinitely away, is going to be parallel. I can't draw this very well. But essentially, wait, here, like this. And then given an infinite distance away, this light is going to be coming in like that. And then let's take another point on here. Let's say here. An infinite distance away, this light will be entering like this. So what do we know about this? This means each pixel on the ground is going to have, light reflecting off of each pixel on the ground is going to be entering our system parallel. Okay, so infinite object distance gives us, can anyone tell me where the image is? Any takers? hit. Remember our Gaussian formula from before was 1 over F equals 1 over SO plus 1 over SI. These derivations are actually all in the STD, but that is quite a chunky document by now. This is, I'm trying to give like, I guess an abridged thing so that people that have worked on different parts of the system can get an idea of the other parts. Okay, so here, SO is infinity. So that means this 1 over infinity is just 0. So F equals SI. So SI is just F. So that means our image forms a focal length away. So this is our focal plane. What goes F, but also the image will form here. What will that look like? I mean, let's say it looks something like this. What would happen with a single lens is the image would actually end up inverting, but the four optics would be designed differently. So we just ignore that aspect for now. So what component do we have here? Here. We have the four optics and then the slit. So what that looks like is, so essentially right here, we would have like this. Like this. And what this essentially does is it acts as what's called a field stop. So field refers to field of view, so what you can see, right? So if you look at this bit, you can find that light coming from, okay, so light coming from the edges of, okay, what you find is that light coming from these parts end up here. Light coming from these parts end up here. So you're actually only accessing like this bit. I haven't drawn where the rays land. You get a little messy, but hopefully that makes sense. So this is where we select, okay, wait, over here. In reality, these would be like 2D, right? If you were to tilt this, you would see how it would be like this. Or actually more accurately, would be like this. But we're just looking at the profile view right now. So here, what you would have is, or on something like this, we've selected, this is light that we're letting through here. Because these parts are all blocked. That's the slit. And then, so now we're just working with this bit. That's kind of the four optics. And why we place the slit in the focal plane, because the image forms here. Okay, so the next thing is just, it's the filter. I won't get into it in detail. I'm just gonna be like, filter. It selects the wavelengths of light that we want to like splat through, right? And then, nope. Okay, I've skipped like collimators and focusers. Actually, I will add them. Okay, so next thing we have is a collimator, which I'll just draw as a lens again, like this. Well, okay, like this. That's an achromat. This is the collimator. That basically, okay, wait, so here, we have light coming from the center here, but the light coming through here isn't parallel. Isn't all parallel, right? Again, it's light from each point enters parallel, but we still have sorry, please scratch what I said in the last minute. So light comes here, light enters this parallel, and that means this will focus it at the focal point. So there, it's no longer parallel, and that's why we need this collimator. So for example, the green rays coming in here, right? What will happen is, because they come from like too far of an off-axis point, let's say like here, they will focus somewhere up here, like that. And then what will have let through by the slit is, let me change colors. Let's say from here we have this will come at like a lesser angle, like this, and then it'll focus. Let's say right here, just passes through. So these rays are no longer parallel. So what they'll do here is they'll propagate like this, right? So what we want to do here with this collimator is output parallel light so that the filter receives the light parallel so that it can do its job. So what do we know here? Again, just simplifying everything to the max. This one is actually reasonably simplified, unlike the 4 optics. We'll just take this as one principal axis. And then if we want parallel light output, like this, then we want to place this at an object distance of, you guessed it, the focal point. Wait, so this is F for optics. This is F of collimator. So then we have the filter, and then we have filtered light going out, still the way it did. And then this is where we get into the prism. Okay, so essentially what the prism does, I actually am going to simplify this again. I'm just going to pretend that it's just a grating. Because a grating and a prism and a grism essentially do the same thing. They just do them in different ways, and some do it better than others. Well, okay, but depending on how you design each, you can also make them better. It's just there's trade-offs when you put something in this kind of form factor. We're just gonna pretend that this is a grating, like sure. Grating. If I write grating, then it looks like a grating. So what we have here is just bundles of light rays that each of the rays carries a range of wavelengths, right? Like whatever. Does that make sense? And then here, what we want to do is pull out those wavelengths. So what happens is we'll have, we'll have an incident ray like that, let's say. And then the grating will output no, I need colors. Okay, let's say like here, here, here. So what that'll do, let's say we have another one and it'll do the exact same thing here. Like this. Pretend that each of these is parallel. So what's happened here is you've taken your incident light and then given each wavelength a different output angle. So for this one, for the yellow one, you have, I drew this poorly. Okay, one sec. I put a ray right here at the axis, that'll be easier to show, like this. Okay, so you can see how the yellow one has this angle. The blue one has this angle, and the green one has this angle. So then we want to map these wavelengths. The goal is we have a detector here, right? Once again, I'm just going to detector. Keeping in mind that all of these go into the page as well. It'll be like this, but I'm just doing profile. We want yellow to land here, green to land here, and blue to land somewhere here, let's just say. So how do we do this? We put another lens, again, achromat. So what we have here is essentially the different wavelengths entering, so yellow like this, and blue like this, and green like this. But once again, it'll be like this, right? Like, and then the okay, the yellow like this, let's say, like that. So what we want is to basically bring all of the yellow together so that they land like this right here, and the same with the blue. So that they land right here, and the green, so that it lands right here, like this. And you can see how this would apply to many wavelengths. Right here, I'm just drawing 3. So what do we know? Once again, this light is parallel, right? Just that fact means that like we don't actually have any kind of infinite distance here at all. But this fact means that we can treat this object distance as infinity because the light is parallel, because that's how the grading outputs it. So then let's go from here. So that means that this distance would be the focal length, right? Focal length of the focuser. Okay, now we have a detector with, okay, you know what? With my yellow wavelengths here, blue here, green here, and what does this dimension have? What does this have? This corresponds to, if we go all the way back here, this bit of light that we let through, but let me use a different color. That's really bad. The tablet has fewer colors, and I have a grievance with that. Let's say this. Okay, so this bit of light that we have in this direction, if that makes sense. Because once again, this object also goes into the page, right? So yeah, well, it's more like this. So this strip of land, nope, it's fighting me. Okay, so this that we let through now corresponds to this. So these are our spatial pixels, right? And here we have the rainbow. I went a couple minutes over time. Let me know if you have questions. In geometric optics, the image point is an infinitesimal point, correct? In which case, would the slit need to have an infinitesimal? Oh, okay. Okay, wait, let me think about this. We do use point sources. Yes. Well, okay, the thing is though, each point is infinitesimally small. You can think of it that way. But when we have like actual extended objects and stuff, right? What we do is just think of it as many point sources. So, well, yeah. So for example, this object that I drew here, right? We can just think of it as, you know, here's my point source, another point source, another point source, another point source. Like, you know what I mean? And then for the slit, the goal isn't to let through, you know, like a single bundle of light. Maybe I gave the wrong impression, but up here, what I was thinking is, you know, this will come from here, but we can have, this is getting real messy. We have another point coming from here that will land here. Like, it's a finite width that we choose to let through. And that corresponds to our spatial resolution. Because if you think for Pushbroom, we're scanning one row of ground at a time, right? So here, these are our spatial pixels, right? And this height here that we let through here is going to correspond to the spatial resolution if we assume these pixels are square. Because, you know, like the rest, oh no, I'm getting too close to the edge of the screen. Tablet is annoying like that. Let me, okay. Hopefully that gives me access. There we go. Okay. I added something. Yeah, so if we have like this, if this is our field of view, I'm just pretending things are square, but you know, these are my pixels. You can see how this, which is the spatial resolution delta, I'm just going to call it delta, a long track. Okay, anyway, I'll just call it delta. Is controlled by this slit width, but this slit width also affects stuff after it as well. Jennifer knows. But yeah, I think that's it. Hopefully that was a helpful overview, because software design document is very long. Everyone's putting in a lot of work, but it's kind of brings stuff together. I'll stop the recording here. Let me know if you have other questions.